Refraction of light. Light rays are refracted at curved surface. Example, lenses. As at flat surfaces, according to the law of refraction of light, unlike with flat surface, though through images are formed, there are two basic types of the lens, concave and convex lenses, which can act as diverging or converging lenses depending on their refractive index relative to surrounding medium. For all diagrams showing image production by refraction, the object is assumed to be the light source, and certain points, together with known facts about light rays passing through them, are used to construct the paths of the refracted rays. The position of objects and images can be determined using the mirror formula or the lens formula. Now let us take convex lens and the concave lens. In the figure, all the lenses shown are considered to be thin lenses. That means the thickness of the lens is small compared to the focal length. That is known as the thin lens. Although light rays bend both on entering the lens and emerging from it, they are drawn as bending only once at a vertical line running through optical center of the lens. So in the given figure, if we combine the two sphere of the glass, okay, then from that we can get the convex lens, first figure, and we get the concave lens, that is the second figure. So in that way we get the convex lens and the concave lens. In the second figure, how the concave lens is made is shown. Radius of curvature. The radius of spheres from which the curved surface are formed are known as radius of that surface of the lens. The radii of the curvature of the two surfaces are taken as capital R1 and capital R2. Principal axis of a lens. An imaginary straight line passing through the center of curvature of lens is called principal axis. So it is the imaginary axis or imaginary straight line. Next, optical center. The center or central point of a lens on a principal axis is called an optical center of lens. It is denoted as O. Principal focus. When rays parallel to the principal axis of convex lens are refracted through lens, they converge at a point on the principal axis. This point is called principal focus of a convex lens. A convex lens has two principal foci, capital F1 and capital F2, on either sides of the lens. The rays parallel to the principal axis of concave lens are refracted such that they appear to be diverging from a point on principal axis. Such point is called focus of concave lens. Concave lenses also has two foci, F1 and F2, on either side of the lens. You can see from the figure. Focal length small f. The distance between optical center and principal focus is called focal length of a lens. It is denoted by small f. So here OF, capital O, capital F, OF distance, that is the focal length, small f, and the distance OC is given by the radius of curvature. So radius of curvature is taken as a capital R. Now another term we are taking. To locate the image formed by spherical lens, a ray diagram is constructed by considering any two of the following rays coming from the object point. So to locate the image formed by the spherical lens, A ray diagram is constructed by considering any two of the following rays coming from the object point. A ray of light from the object parallel to the principal axis of convex lens passes through the principal focus after refraction from convex lens on either side of the lens, figure A. In case of the concave lens, the ray appear to diverge from the principal focus located on the same side of the lens as the object, figure B. A ray of light passing through a principal focus after refraction from a convex lens will emerge parallel to the principal axis. See the next figure, in which when the rays passing from the F and incident on the lens, then after refraction it will become parallel to the principal axis. A ray of light moving towards the principal focus of a concave lens will emerge parallel to principal axis, figure B. In this, what happen if we are taking the concave lens, then the rays coming and incident on the concave lens after refraction, it will become parallel. It will become parallel to the principal axis. A ray of light passing through the optical center of convex or concave lens will emerge without any deviation. See the next two figure, in which if you are taking any convex lens or the concave lens and the rays passing from the center of convex or concave lens, then without deviation or without refraction it will pass from the optical center in the same direction. So, this is the figure shows this thing. Now, let us take how the image formed by the convex lens. So, here in the first figure we have taken the position of the object at infinite distance, means the light rays are coming from the object which is kept at very large distance. So, the light are coming from the object from infinite distance. The position of the image is what? On the other side of the lens at principal focus. The nature of the image is real and inverted. The size of the image is highly diminished point size. That means the rays which are coming from infinite distance, they are parallel rays, they are parallel to each other and it is known as the parallel rays, and when they incident on the convex lens, after refraction all they are get converge at the principal focus F. So, we get the highly diminished image size, point size image, in real and inverted image. The second figure indicate object is beyond 2f. So, what is the position of the image? It is on either other side of lens between principal focus F and 2f. The nature of the image is again real and inverted. The size is smaller than the object. So, in this figure when we kept the object beyond 2f, then let us take the AB object, it is beyond 2f1. Then the ray diagram, in that we take the minimum two rays which is coming from the A and incident on the lens, and after refraction they will meet at the A dash point. The another rays coming from the B point meet at the B dash point after refraction. So, we get the A dash B dash image which is real and inverted and smaller than the object. Now, let us take another case in which the object position at the 2f on the other side. So, how the image is formed? When you kept the object on the 2f, then we are taking more than one rays. Okay, so two rays we are taking minimum coming from the A and incident on the lens. After refraction it will pass and it will meet at the A dash point. Same way from the B point also we get the another ray which is passed from the optical center. Without deviation it pass from the O and it meet at the B dash. So we get the image on either other side of the lens at 2f position. The nature of the image is real and inverted, and the size of the image is same as that of the object size. So keep in mind, when we kept the object on 2f, then we get the image at other side on the 2f, as well as its size is also same, but image is real and inverted. The another condition, the object is kept between f and 2f. In that condition, by using the ray diagram, we get the image position beyond 2f, and the real and inverted image we get, as well as the size of the image is magnified, enlarged. Here you can observe, then as you put the object nearer to the lens, you get the enlarged image. So in this way you can draw the ray diagram. Now let us take the another condition of the object. If the object is kept on the principal focus, then what is the position of the image? In that case, the rays coming from the object are incident on the lens, and after refraction all the rays are become parallel to each other. One rays is, you can see from the figure, passing from the f2, other ray is directly passing from the optical center O, and these two rays are become parallel to each other because you have put the object on the focus. So the position of the image is at infinite on the other side of the lens. We get the real and inverted image. The size of the image is again magnified, enlarged image. Another condition of the object, we can put the object between f and the optical center, means between the principal focus and optical center. So in that case, here also the object is very nearer to the lens. So according to the ray diagram and according to the law of refraction, one ray, you can see from the figure, it is passing from the optical center O, and other ray is passing between f2 and 2f2. As they are not parallel, then they are appear to meet at the same side of the object at the A dash point. So we get A dash B dash as a image, but it is at the one side, image at the side of the object, it is the virtual image. Okay, so position of the object, is between principal focus and optical center, then position of the image on the same side of the lens as the object beyond 2f. The type of the image nature is virtual and erect, and the size of the image is magnified or the enlarged image. So in this last case, we get the enlarged image as we put the object between optical center and principal focus. So we get the enlarged image, virtual and erect image, and at the same side. What is the meaning of the virtual image? The image which cannot be obtained on the screen, that is the virtual image here. So these are the 6 cases of the convex lens in which we have put the object between different position and we get the image at the other side of the lenses, and we get the two type of the image, real and virtual. Now let us understand converging lens. What is the converging lens? A lens which causes parallel rays falling on it to converge on the principal focus on the other side of the lens. Both concave and convex lenses can act as converging lenses depending on the refractive index of the lens relative to the surrounding medium. A glass convex lens in air acts as a converging lens as shown in the diagram on the right side. So, in this diagram you can see that the light rays parallel to the principal axis incident on the lens, convex lens, and the refracted rays are converged and they are meet at the point F. So, refracted rays meet at the principal focus in front of the lens. Now, in the same way we can take the diverging lens. What is the diverging lens? A lens which causes parallel rays falling on it to diverge so that they appear to have come from the principal focus on the same side as the rays enter. Both concave and convex lenses can act as diverging lenses depending on the refractive index of the lens relative to the surrounding medium. Understand this sentence. A glass concave lens in air acts as a diverging lens as shown in the diagram on the right side, in which the light rays parallel to the principal axis incident on the concave lens and after refraction they diverge from each other, but they are appear to meet on the F at the side of the parallel rays. So, here we get the concave lens as a diverging lens. Now, let us talk about the convex lens and concave lens. Convex lens, a lens with at least one surface curving outward. A lens with one surface curving inward and one outward is convex if its middle is thicker than its outer edge. It is a convex meniscus. A glass convex lens in air acts as a converging lens. The size, position and type of the image it forms, real or virtual, depend on how far it is from the object. You can see the type of the convex lens as a biconvex, plano-convex and convex meniscus, and there is one example given. When the object is kept between O and F dash, then image is seen behind the object and is upright, larger than object and a virtual image. Now, concave lens, a lens which has at least one surface curving inward. A lens with one surface curving inward and one outward is concave if its middle is thinner than its outer edge. So, it is a concave meniscus. A glass concave lens in air acts as a diverging lens. The position of the object in relation to the lens may vary, but the image is always on the same type. So, there are the few types of the concave lens: bioconcave, plano-concave and concave meniscus. One example is given of the concave lens. When the object is kept at the other side of the convex lens, we get the virtual image. So, in this way we can know about the convex and concave lens. Now let us talk about the sign convention for spherical lenses. For lenses we follow sign convention similar to the one used for spherical mirrors. We apply the rules for signs of distance, except that all measurements are taken from the optical center of the lens. According to the convention, focal length of a convex lens is positive and that of a concave lens is negative. You must take care to apply appropriate signs for the value of u, v, f, object height h and image height h dash. What is the lens formula and magnification? as we have a formula for spherical mirrors, we also have formula for spherical lenses. This formula gave the relationship between object distance u, image distance v and the focal length f. The lens formula is expressed as 1 upon small v minus 1 upon small u is equal to 1 upon small f. Means 1 upon v minus 1 upon u is equal to 1 upon f. The lens formula given above is general and is valid in all situations for any spherical lens. Take proper care of the signs of different quantities while putting numerical values for solving problems relating to lenses. So, here we are using the 1 upon v minus 1 upon u is equal to 1 upon f equation. Now, magnification. The magnification produced by a lens similar to that for the spherical mirrors is defined as the ratio of the height of the image and the height of the object. Magnification is represented by the letter small m. If h is height of the object and h dash is the height of the image given by the lens, then small m is given by ratio of the height of the image to height of the object is equal to h dash upon h. Magnification produced by a lens is also related to the object distance u and the image distance v. This relationship is given by magnification m is equal to h dash upon h is equal to v upon u for the given lens. Now let us understand what is the power of lens. You have already learned that the ability of a lens to converge or diverge light rays depends on its focal length. For example, a convex lens of short focal length bends the light rays through large angles by focusing them closer to the optical center. Similarly, concave lens of very short focal length causes higher divergence than the one with longer focal length. The degree of convergence or divergence of light rays achieved by a lens is expressed in terms of its power. The power of lens is defined as the reciprocal of its focal length. It is represented by the letter capital P. The power P of a lens of focal length small f is given by P is equal to 1 upon f. The SI unit of power of lens is a diopter. It is denoted by the letter capital D. If f is expressed in meter, then power is expressed in diopters. Thus, 1 diopter is the power of lens whose focal length is 1 meter. So, 1 diopter is 1 meter inverse. You may note that the power of convex lens is positive and that of a concave lens is negative. Opticians prescribe corrective lenses indicating their powers. Let us say that the lens prescribed has power equal to plus 2 diopter. This means the lens prescribed is convex. The focal length of the convex lens is 0.5 meter. Similarly, a lens of the power minus 2.5 diopter has a focal length of minus 0.40 meter. So, that lens is the concave lens. So, dear student, in this way here you understand all the terms of the lenses, concave lens, convex lens, their terms, formulas, lens formula, power formula, magnification, and the cases in which the object kept at the different position and we get the image at the different position either side of the lenses, and we get the real and inverted type of the image and virtual or erect type of the image. So, in this way here our theories are completed for this chapter. Okay, thank you. very much.